Welcome back to lesson number 5, where we start to analyze and model each of the quantities that appear in the multi-component gas-liquid equilibrium equation. We have seen last time how to write the equilibrium equations. We have seen it for a pure component gas phase, leading to what we call the solubility of that component in the liquid. And we have seen it for a multi-component gas phase, leading to the more general concept of saturation of a gas in a liquid phase. The next step will be that of solving the equilibrium equations. To do that, we need to express each one of the quantities that appear in those equations, and that we have seen to be the fugacity coefficient for each volatile component in the gas phase, and the reference fugacity and activity coefficient for each volatile component dissolved in the liquid phase. Let's see how to find such expressions, and let's start with the fugacity coefficient, which is the subject of this lesson. Okay, first of all, let's make a recap of the concepts and equations that led us in the previous lessons to the definition of fugacity and fugacity coefficient. They stem, as anything else in this entire training module, from the combination of the first and the second laws of thermodynamics. By combining the first and second laws, and through the Legendre transformation, we defined 4 different but equivalent versions of the fundamental equation expressed in terms of differential changes of internal energy, enthalpy, Helmholtz energy, or Gibbs energy. In particular, in equilibrium problems, we make large reference to the Gibbs energy, just because Gibbs energy is expressed in terms of pressure and temperature, and that matches our experience. It corresponds to how we approach our problems, both theoretically and in the laboratory. We showed that the chemical potential mu is nothing else than the molar Gibbs energy for a pure component, or the partial molar Gibbs energy for a component in a mixture. From that expression, the pressure partial derivative of the chemical potential turns out to be the molar volume. For ideal gases, we could therefore derive a simple expression for the chemical potential. Lewis extended that expression to any substance in any state, either pure or in a mixture, by replacing pressure with fugacity. That operation gives us a definition of fugacity, which is nothing else than a corrected partial pressure where the correction factor embeds the deviations from ideal behavior, and it's called the fugacity coefficient. If you want to refresh your memory to all of these, you just have to look back to lesson number 3. Okay, we now know what is the fugacity coefficient. It is a correction factor that expresses the difference between real fugacity and ideal partial pressure. Now, in order to use the fugacity coefficient in practical computation, we must be able to compute it for any possible condition of our interest. This is what we are about to see. What makes it easy with ideal gases is that we know an expression for the molar volume, what we call an equation of state, which relates volume to the specific pressure, temperature, composition conditions. Note that here the composition of the specific gas is included in the numerical value of R, the gas constant for the specific gas under consideration, which is given by the absolute gas constant divided by the molecular weight of the gas. Knowing how to express the volume of gas, we can substitute it in the derivative of the chemical potential, integrate it, and obtain a simple expression for the chemical potential of an ideal gas. If we had a similar expression, an equation of state, for the molar volume of the real gas, we could repeat it, this time with the molar volume of the real gas, and by integrating it, we would have solved our problem. What we need is therefore a real equation of state describing the volume, pressure, temperature relationships for the real gas of our interest. Fortunately, the behavior of many real gases has been studied in depth and for a long time, for obvious reasons. In fact, real behavior is the normal condition in the real world. Ideal behavior is only approached when the interactions between the molecules forming the gas become negligible. That happens when the molecules are sufficiently far from each other, as in the example on the left. Or in other words, when the gas is sufficiently expanded. That's why any substance behaves ideally in the limits of zero pressure. For any other situation, the assumption of ideal behavior is just an ideal reference, giving us an approximation that, depending on the conditions and on our specific problem, can be or cannot be justified. In general, the real world is real. Therefore, real equations of states are needed to properly explore the real world. That's definitely true when dealing with natural magmas that exist at extremely high pressure conditions within the Earth's crust. It is also true in a very large number of other applications in chemistry, engineering, earth sciences, and so on, what has triggered systematic measurements of the volume and other properties of real gases, either pure or as a mixture of a wide range of conditions. Such huge efforts by legions of scientists have produced several real equations of state, often indicated by their acronym EOS. Such EOSes aim at including the relevant effects of molecule interactions, and they present themselves as modifications of the ideal equation of state by inclusion of additional terms that have the scope of accounting for such real effects. Among the most famous equations of state proposed for real gases, you probably heard already some of them, some reported here, which are just examples of some of the most famous and widely used EOSes out of many existing. Each one of them provides an expression for the gas volume as a function of pressure and temperature, and it involves a number of parameters that are defined from laboratory measurements. In the case of gas mixtures, that is, gases made of more than just one component, like the water plus carbon dioxide gases that we are interested in, a specific equation of state is defined with terms and parameters adequate in the pressure, temperature, compositional range of interest, implying that heavy measurement cycles must be done by not just varying pressure and temperature, but for any pressure, temperature condition, by also varying the relative amounts of each component in the gas. Fortunately, as I anticipated, water and carbon dioxide are not only the most abundant volatiles in magmas, they are also among the most common and most relevant molecules on the Earth's surface, in the oceans, and in the atmosphere, and they are fundamental for life on Earth. That helps substantially, as we can benefit from an enormous volume of data provided by a multitude of scientists whose hard work led to the definition of quantities and equations of state adequate for our purposes. In fact, equations of state exist for gaseous mixtures of water and carbon dioxide, covering from atmospheric temperature to 1,000 degrees and from atmospheric pressure to gigapascals. Some of them are better for some respects, and some others are better for some other respects, of course. Commonly, the choice of one or the other involves a balance between accuracy, easiness of implementation in a computational code, and computational costs in terms of time required for the computation. So, what an equation of state does is to provide us with a relationship between volume and pressure, temperature, composition, conditions for the gas under investigation. Given such an else, we can integrate it as we did for ideal gas, now, of course, with a more complex relationship for real gas behavior, and come up with an expression for the chemical potential. That's fine, but we have written the chemical equilibrium equation in terms of fugacity. And to solve it, we need an expression for the fugacity coefficient phi. How do we obtain the fugacity coefficient from a real equation of states? Here is an exercise for you. As usual, you can either try to solve it or skip it and continue the lesson. In both cases, you will see the solution in the following. The exercise is this one. Write an equation for the fugacity coefficient phi in terms of real volume of gas. I give you a suggestion here. Just refer to a pure gas, which makes the problem easier. Start from the definition of a quantity, which represents the difference between real and ideal molar volume. Then use the relationship between chemical potential and molar volume. Press pause now if you are doing the exercise. Here we go. Let's refer, for simplicity, to a pure gas, that is, a gas made of just one component, like pure water or pure carbon dioxide. The reasoning is completely general, and at the end I will generalize it. But in order to see the development of the equations, the pure component case is simpler, and it helps us following the reasoning. Just define a convenient quantity, psi, equal to the real molar volume of the substance, V, minus the ideal molar volume, which is given by the ideal equation of states. Clearly, for an ideal gas, psi is equal to 0, while for a real gas, it will be different from 0, describing the deviation from ideal behavior. From the definition of psi, we can then write the real volume in terms of psi. Now we have an expression for the real volume that we can use inside the expression for the chemical potential. By integrating, we obtain the chemical potential in terms of our newly defined quantity psi. The chemical potential for a real substance, we know it, is also equal to this other expression. We know that since when fugacity was first introduced in lesson 3. We can therefore equate the two expressions and obtain this one. Here I have simply cancelled out the term mu0, which appears at the right and left hand side of the equation. Finally, by moving all the logarithmic terms together and combining them, we obtain this last expression. I report it in this new slide. Note that at the left-hand side, we have both pressure and fugacity, both of them referring to system conditions and to reference conditions, the latter indicated with a 0 at the apex. Now let's take another convenient choice. Let's choose a reference pressure approaching zero pressure. By the definition of fugacity, at zero pressure, fugacity and pressure coincide. You remember that fugacity is a corrected pressure which expresses the deviation from ideal condition. Therefore, at zero pressure, where the behavior is ideal, fugacity and pressure coincide. Therefore, at the reference state approaching zero pressure, F0 is equal to P0 and they cancel out. So we obtain this new expression. Now we just substitute the definitions for the fugacity coefficient phi and for the term psi that we have introduced above, and we obtain the expression for the fugacity coefficient that we were looking for. Let's have a look at it. We see that the fugacity coefficient that we introduced in lesson 3 to account for the deviation from ideal behavior relates, in fact, to the difference between the real molar volume of the substance, V lowercase, and the corresponding ideal molar volume. Such a difference is not just evaluated at certain conditions. It must be computed as the sum, or more precisely, the integral, of all of the differences between real and ideal volume along the whole path from zero pressure, where the substance behaves as ideal and the difference between the real and ideal molar volume is 0, up to system pressure P. We clearly perceive from this expression how the fugacity coefficient expresses the deviation of a substance from ideal behavior. Very important, remember that integration must be done at constant temperature, equal to system temperature, in order to satisfy the definitions of chemical potential and fugacity, as we know well from lessons 2 and 3. In summary, in order to compute the fugacity coefficient, we need an equation of state describing the real volume of the substance from its ideal conditions approaching zero pressure up to system conditions. Once we know that, we can compute the integral of the difference between real and ideal behavior along the whole path from 0 to system pressure at constant temperature equal to system temperature, and that operation gives us the fugacity coefficient. I have derived the expression for the fugacity coefficient of a pure substance, but I anticipated that the reasoning is completely general. It also holds, with minimum adjustment, for a component in a mixture. Here it is. In this case, instead of the real molar volume of the substance, we have the real partial molar volume of the component. For example, the partial molar volume of water in a gaseous mixture of water and carbon dioxide. Again, we need a real equation of state, this time for the water-carbon dioxide mixture, from which we can express the partial molar volume of the component of interest, again from zero pressure, where its partial molar volume is equal to the ideal molar volume of the pure component, up to system conditions. Let me open a bracket here. It is useful to remind what is a partial molar quantity, the definition of which I gave in lesson 2. A partial molar quantity refers to a given component and is obtained by the corresponding total mixture quantity, partially differentiated with respect to the number of moles of the component. This is the corresponding expression for the case of partial molar volume. In other words, the partial molar volume of, say, water in a gaseous mixture, or of carbon dioxide in a liquid magma, or of any other component in whatever mixture, is the total volume change due to the addition or removal of an infinitesimal amount of that component, which is added or removed without changing pressure, temperature, and amount of any other component in the mixture. By this definition, it follows that partial molar quantities only apply to extensive variables. That is, variables whose value depends on the amount of matter. For example, pressure and temperature are intensive quantities, and there is nothing like a partial molar pressure or a partial molar temperature. Conversely, volume, entropy, enthalpy, and any other energy form, such as Gibbs energy, are all extensive quantities. Therefore, there are corresponding partial molar quantities. We have seen already that the chemical potential of a component in a mixture corresponds to its partial molar Gibbs energy. For a pure component, the partial molar and the molar quantities obviously coincide. Okay, bracket closed and lesson close to its end. Now we know how to deal with one of the key quantities in the equilibrium equation, namely the fugacity coefficient of each component in the gas phase. We simply need an equational state describing the real volume from ideal conditions approaching zero pressure up to system pressure. We integrate its difference with respect to ideal volume along an isothermal path corresponding to system temperature, and it's done. In the next lesson, we will get through another key quantity in the equilibrium equations, namely the reference fugacity of volatiles in the liquid phase. Step after step, we are constructing our real multi-component thermodynamic equilibrium model for volatiles in magmas. And that's emerging by just employing the first and second laws of thermodynamics and nothing else. That always strikes me, to see how big consequences derive from such simple laws. You will see it even more within the next lesson. See you there.